pick up? Okay, so relative humidity is the easiest to measure. How close are you to being saturated, basically? So just to kind of summarize, we said we can change the temperature, and that's going to change your relative humidity. If you decrease the temperature, basically your air can hold less water, and so that's going to increase your relative humidity. Okay, if you increase your temperature, when you go to the table, actually you're going to come up with a larger number, and then your percent relative humidity is going to be divided by a larger number, so that's going to lower your relative humidity. Okay. I think I mentioned before with that picture with the fog. Basically, fog is liquid water, okay, and the reason it liquefied was because you cooled it down to the dew point temperature, basically. The other day, this is a true story, my husband got up after that bad fog that kind of broke about midnight, I think. Our daughter was out in it, and she was fine, but he got up in the morning, he's like, oh, because our Roku, when it goes into sleep mode, it like shows the atmospheric conditions, just the weather thing. It's like, oh, percent relative humidity is 65%, so the fog must have gone, and he's right. But he just thinks he's so smart. But the other thing was there was a little bit of wind too, and fog, as you may know, wind will disfavor the formation of fog. So there you go. So you guys are going to kind of have a homework question about this. This first one is you kind of see as throughout the course of a day what the temperature does. No surprises. This is what we talked about in Unit 2. We said that, Unit 1, excuse me. We said that it's coldest right at dawn, okay, and then we have that lag of maximum. So, wow, this is showing, clear till 6 p.m. till you have your highest temperature. I'm thinking it's more like 3 or 4 p.m., okay, but that's your lag of max. But now, if we were to assume that the water vapor in the air stays constant, based on what the last slide said, does this make sense to you? When it's coolest, actually, we're going to have our highest relative humidity, and when it's warmest or hottest, we're going to have our low relative humidity. I know that seems backwards, but when it's hot, the air can hold more water vapor, so it's lower relative humidity. So that's what this is. So basically, if you match up what color do I want to check? If you match up the hot part of the day, actually that's the lowest relative humidity. I know it's like, no, because it's all, and it's true, that the sun actually can end up adding more water vapor to the air, but assuming you don't add more water vapor to the air. Okay, and right about dawn, well, if you go camping, oh my gosh, right about dawn when you're getting up, that's when everything's like so sticky, and you have like kind of a blanket of dew over everything. Okay, it's because you have high relative humidity. Ah, yes. I like that video because I like seeing just ready for spring, ready for summer. So we're kind of finishing up ways to gauge humidity in the air. One of my things I've never seen a device like this, but basically if you have it's summertime and you have a cold beverage, if you're outside and your beverage is iced down, okay, it's going to sweat on the outside. But what's happening though is basically water is condensing there. Like water from the air, it's high enough humidity that basically it's going ahead and saying it's cold enough right around your glass, I'm going to go ahead and condense. You've reached the dew point temperature around here. So my thing is, if the air is kind of dry, okay, so basically your dew point temperature is really pretty low, okay, your glass is not going to sweat. So I think we can use our beverages as, really you can. So a high dew point temperature, think what that is. A high dew point temperature means that you're bumping up against the current temperature. So you're only pretty humid, okay? A low dew point temperature, okay, means you have to march, you have to cool it down a lot. So that means that your air is relatively dry. I like things that make sense, and that makes sense to me. So doesn't this make you hungry and thirsty and, yeah. So like I said, that's an indication of the water vapor in the restaurant or outside. And then does this make sense? In the wintertime, we run our humidifiers, and your textbook talks about this, okay? Because the air in our houses basically came from outside, because you can't have a sealed up house, okay? It's got to breathe. Okay, so the air is coming from outside, and the air outside is really pretty darn dry, and so it makes here, okay. In the summertime, it's the opposite. We run a dehumidifier, okay, because it's pulling in warm, moist air from outside. And that's why, like, your air conditioners, they condition the air. They not only cool it down, but they also take the humidity out, and they can get kind of messy if you don't have the little drain thing from your air conditioner going into the right place. All right. So the dew point temperature is a place at which you'll reach 100% relative humidity. So the dew point temperature. And so if it's relatively high, that means you probably have oppressive conditions. Okay, terrible. Okay, if it's relatively low, then it's very dry. So these look like isotherms. Remember, isotherms was a map that basically connected locations at the same temperature. But these are connecting locations with the same dew point temperature. And these look like they're in units of Fahrenheit. So, for instance, the whole yellow thing, the dew point temperature is 20 degrees Fahrenheit. So you're like, dude, that's pretty low. That's pretty darn dry there. Okay, compare that to 70 degrees. Okay, very humid. And it looks like we are kind of here-ish about 55. It's our dew point temperature. To me, it doesn't, what this map is missing, if you're like me, is, okay, so if our dew point temperature is 55, what's our current temperature? You know what I'm saying? It's like, if we're at 60, but if we're at 80, so. All right, so, good. Measuring relative humidity. Actually, I brought some gizmos here so we all get to measure relative humidity. Okay, so how much water vapor is there? And again, the whole, I'll emphasize relatively speaking. Relative humidity is basically kind of compared to saturation. I have a picture here of a hair hygrometer. Those of you who have long hair, or if you know somebody that has long hair and it gets curly or not curly, depending upon the humidity, that's the technology used right here. It's probably horsehair, not human hair. But basically, does it curl up under high humidity, and then low humidity is length, something like that. Okay. So, let's see. Sensitive to changing. Hair expands as humidity rises and contracts as humidity decreases. So hair expands, high humid. As it gets drier, so you can turn that into like just making that needle move. So then I have a couple of pictures of electric hygrometers. The word hygrometer means a device to measure humidity. And so here are a couple of electrical ones. Okay, but I want to spend a little bit of time talking about the psychrometer. And I brought, these are psychrometers actually. Okay. So these psychrometers, and I'll go ahead and, they all have to have a little sock on them. 3, 4, or just like this. This is what's being described. Basically, you have 2 thermometers, and one thermometer underneath it has a little sock that you're going to wet for a minute, and the other thermometer is dry. And they're called a Sling Psychrometer because you're going to sling them around. Okay? That's the slinging part of a Sling Psychrometer. Okay? So, here in a minute when you... This one doesn't have a sock. Or did my sock fall? Here in a minute, I'm going to go ahead and bring around a cup of water. And you're going to dip your both thermometers... Or, no. I guess just dip the thermometer that has a sock. Dip that one in the water. You're going to keep the other one dry. Okay. So here's the deal. The one that's wet. Okay, so this is going to be wet. Now, liquid water evaporating, okay, it's actually going to use up energy. So, use energy, and it's going to cool the environment. Do you remember we talked about sweating and the heat index, and we said the reason the heat index, or the reason we sweat is to go ahead and cool us off. Basically, we're hot and we're expecting the liquid to go ahead and evaporate. As it does so, it cools our skin. Okay. So the problem with that is the more, and this is exactly why these Sling Psychrometers work, if it's already humid, if there's already a lot of water vapor, then that whole evaporation process can actually be stunted or shut down. So it won't evaporate. So here in a minute, when you sling these around, okay, if the humidity is pretty low, you're going to have a lot of evaporation, and it's going to have a big cooling effect. Actually, you're going to see this temperature go down. Okay, if the humidity is low. If the humidity is high, it's not going to cool, and basically these two thermometers are going to match. That's it. That's totally it. Okay. All right. Do you need to fill any of those? All right. So here we go. So this is just deionized water. So if you can kind of just isolate the one that has a sock and dip that one in here, and then swing it for, I don't know, 20 seconds, and then stop and then jot down what your thermometers read. Just jot down the dry limits. And then I'm going to go around and I'm going to have you tell me what you got. I'm going to start with the dry bowl, the one that didn't have a sock, and then tell me what the wet one was. Dana. It's hard to read sometimes. But so what was your dry thermometer? 22. 22? The wet one?
19.
19? Good deal.
Mine was 22 for the dry and about 18 for the wet.
18? Good deal. Okay.
I also had 22 over 18.
Very good. Okay. So they were similar, but we definitely had a cooling over here. Okay. So if we went with 22 and 18. All right. So now, in order to interpret that, you need a table. And actually, the back of your textbook, I think, has these tables that I'm going to show you. They look like this, not exactly like this. So the way these tables work is along the y-axis over here, we are going to find, what, 22? Okay. And then along the top, we're going to find what we call the depression, or the difference. So actually, along the top there, we need to find what, 4? So the difference is 4, the depression. And then what you do is you see where they intersect, and this table tells us the dew point temperature. So let's see. We said 22 was our dry bulb, and 4 was our depression. So I'm getting 16 degrees Celsius. So if we were to cool this room down 6 more degrees, we'd get all slimy. Okay? This next one is kind of similar, but instead of dew point temperature, it gives you relative humidity. But it's just like the same deal. So along the top, we're going to pick off 4. That's our depression. And along the side, we're going to pick off our dry temperature. And so in this room right now, we are at 68% relative humidity. Not bad. So that's it. Pretty cool. Okay. I think that's where we should do this. Yeah, so let's go ahead and call that a night. That's perfect. Okay? But like I said, I'm going to take a minute to get set up, and does anybody think you're going to stay or going to head or?